I'm Doug Fearn, and this is my take on music recording. How do vacuum tubes work? Tubes are one electronic device that you can actually see how they operate. I explained vacuum tube fundamentals in this conversation with Matthew Glosson. Matthew has been working for D.W. Fearn for the past year, mostly with Geoff Hazelrigg on the manufacturing side of the business. Recently, he constructed some prototype circuits for me as part of my new product development. Matthew recently graduated from the University of the Arts in Philadelphia with a degree in music technology, among other things. He just completed a prototype that was part of an investigation into a possible new product concept, and he was curious about the circuit and why I did certain things. As he was on his way in for us to discuss that, it occurred to me that our conversation might be of interest to you. This is a recording of our impromptu lesson on how tubes work. I really didn't have anything planned, so this is quite informal, and I would probably explain things a bit better if I had prepared more, but I still think it's useful. The recording is less professional than I would have liked, but we were on opposite sides of a ribbon mic far enough apart to properly social distance. You can hear the HVAC and other extraneous noise, including my dogs. A few drawings are available for this episode under Extras at the top of the page on my podcast website, dougfearn.com. All right, Matthew, we're going to talk today about tubes and tube circuits. And I wanted to start out with the most basic stuff, and then we'll gradually build on that. Certainly not going to be a complete course in vacuum tubes, but just an introduction to it.
Mm-hmm.
You know, I'm not totally sure how much you know.
Mm-hmm.
I know you're pretty knowledgeable, but, you know, there's always new things to learn.
Oh, yeah.
I'm going to start out real basically.
Mm-hmm.
And I'm going to ask you a lot of questions.
Okay.
And it's mainly just so I can get a sense of what you know. And it's also, I think, helpful to the listeners because we don't want to skip over something that's pretty fundamental that they need to understand. You know, Thomas Edison almost invented the vacuum tube. I don't know if you were familiar with it. You know, he was experimenting with a light bulb, and the light bulb was carbon or whatever from the filament of the light bulb was being deposited on the glass and gradually making the bulb dimmer and dimmer because it blocked out the light. So he was experimenting, and he put another element in the tube, piece of metal in there, to see what would happen. And what he discovered was that the electrons from the filament were being attracted to this other element in there. And basically what he did was invent the diode vacuum tube. But he saw no practical use for it.
Yeah.
And, you know, funny, I mean, he had enough credits. He didn't really need that. But had he pursued that, he could have added that to his long list of things he invented. So we're going to start with a diode because that's the most basic of the vacuum tubes.
Sure.
All vacuum tubes are called vacuum tubes because...
Oh, because it's a vacuum inside of the tube. There's no air in there.
Right, no air. And that's also a necessity for a light bulb. Can you explain why?
Is it the same reason that a vacuum tube has to be a vacuum?
Well, partially, yeah.
Okay. It's it allows the electrons to travel easier, right? If it's a vacuum, or is it?
Yeah, well, that's true, but when we're talking about light bulbs, we don't care about the electrons.
More about the heat?
Well, think about it. You've heated up this piece of metal in there, which is the filament, and it's going to combine with the oxygen in the air if it's just in air. And pretty quickly, what's going to happen? It's going to burn up.
Yeah.
You know? So what Edison discovered, and I think this was probably pretty common knowledge even before he did this, was that to prevent oxidation, you got to remove
the oxygen.
Yeah. And air is 20% oxygen. So by removing the air, the filament didn't burn out, or at least didn't burn out instantaneously.
Yeah.
You know, eventually it will. What Edison discovered and other people built upon was the fact that when that filament's in there, it's not only emitting photons, which are light, but also, light, not only visible light, but infrared light, which is the heat part. But it's also emitting electrons.
Yeah.
And those electrons will just sort of sit there in a cloud around the filament in a light bulb and really have no function or effect or anything. But if we put another piece of metal inside that vacuum tube and then put a positive voltage on that, what happens?
The electrons are attracted to that.
Right.
Yeah.
And why are they attracted?
Because they have an opposite charge.
Right.
Yeah.
Yeah. Electrons are negatively charged, and the plate which we'll call a plate, which is the common term for that, has a positive voltage on it.
Yeah.
So the electrons are attracted from the filament to the plate. And when you have a movement of electrons, what do you have? I mean, that's just sort of the fundamental definition of an electric current, right?
Okay, yeah. Yeah.
So there's, assuming there's some external circuit, there's a flow of electrons that go from the filament to the plate.
Yeah.
Plate's also sometimes called an anode, which is actually a more technically correct term, but nobody uses that term.
Yeah.
Well, the interesting thing about this is that the electrons go from negative to positive.
Yeah.
They can't go the other way. They can't go from the plate back to the filament.
Yeah.
Right? So it's a one-way street for the electrons.
Yeah.
Here's where Edison missed his opportunity, because the advantage of a one-way conductor like that is you can turn alternating current into direct current.
Yeah.
And the device that does that is called?
A rectifier?
Yep.
Yeah.
He essentially invented a rectifier, but didn't know he did.
Yeah. Yeah.
But other people soon figured that out, both in the U.S. and in Europe. The technology was pretty crude back then, and it was difficult to get a good vacuum. So these weren't very usable devices, but the concept was there.
Yeah.
And then somebody, and it's a little bit controversial exactly who, because I think multiple people came up with this idea pretty much at the same time, that if you put a third thing in between that filament and the plate, it could act as a gate or a valve to control the number of electrons that went through there.
Yeah.
Not mechanically,
No, yeah.
but electrically. Because if you put a negative voltage on that intermediate element called a grid, it becomes like the handle on a faucet.
Yeah, sure.
The more negative you make it, the more you're turning off the water or you're turning off the electron flow. It actually took a surprisingly long time for people to understand the whole significance of that. The earliest vacuum tubes were just used as radio detectors, just the diode as a sensitive radio detector, because converting a radio frequency wave to audio is just a matter of rectifying it.
Yeah.
That was the first application. And then when the concept of the grid came along, it made things a little more useful.
Yeah.
Because suddenly you could control the number of electrons that went through. So far we've been talking about tubes as a filament, an anode, and now we're talking about a grid. But, if we look at the schematic diagram of a diode, that's conceptually very good at understanding what it's doing.
Yeah.
It doesn't describe how it's constructed, although earliest tubes look almost like that, which is, I guess, where the schematic symbol came from. But in this case, if you look at a schematic symbol of a diode, you have a filament and a plate with a circle around it indicating the envelope of the tube, which has a vacuum. The filament is emitting the electrons, which works fine. But they soon discovered that if you coated the filament with some other elements, that you could enhance the number of electrons that were emitted.
Okay.
So that improved the efficiency considerably. And then somebody had the brilliant idea of instead of heating up all this mass with the filament with all this junk coated on it,
Yeah.
which, works, but wasn't totally efficient. If you put something around that filament that would act as only an electron emitter when it was heated by the filament, you had a more efficient tube.
Yeah.
And that other element was called the cathode. And so now the vast majority of tubes that we use are like that. They're called indirectly heated cathode tubes. Okay, so if the filament's doing the job of emitting electrons, it's called a directly heated filament. And if there's a cathode, then that's the electron emitting part. And that's shown on the schematic diagram, as this thing that sort of wraps around the filament. Yeah. Now, have you ever taken apart a vacuum tube?
Taken apart? No.
No?
No.
We'll have to do that sometime.
Yeah.
That's real interesting. They're shown in the schematic diagram as sort of this linear thing. There goes filament, cathode, grid, plate. But actually in a tube, they're arranged concentrically. So at the very center of the tube is the filament. And then the cathode is a cylinder around it.
Okay.
And then there's another cylinder for the grid. And then another cylinder around that for the plate. And that works great because that way you capture all the electrons.
Yeah.
Because, you've got stuff all around everything. The grid in a triode is shown in a schematic diagram as a dashed line, which, explains a little bit about its function because it's not a solid piece. It's something that the electrons can pass through.
Pass through, yeah.
So if you take apart a tube and you look at the grid, it's usually a coil of very fine wire on a framework around the cathode. That's the key to making a vacuum tube work.
Yeah.
Most efficiently. In order to regulate the number of electrons traveling from the cathode to the plate, you can use a varying voltage on the grid. And if there's no voltage on the grid, just like it's not there, it doesn't do anything.
Yeah.
I mean, it may do a little because, it's sort of acting like a little miniature plate. But if it's not connected to anything, it doesn't do anything. But if we put a negative voltage on that, the negative voltage on the grid encountering the negative electrons from the cathode, what do you think happens?
It's going to slow them down, I guess would be the way to say it, or block them, sort of.
Yeah. You could think of it as slowing them down, but they really still go, pretty darn fast.
Yeah. Yeah.
Instantaneous for all practical purposes. So it's not so much that it slows them down, but it does regulate the number they get through. Because when you have a negative electron encountering another negative charge, it's going to say...
It's going to repel.
Right,
yeah.
You won't get as much through. And if you put enough negative voltage on there, what do you think happens?
It would repel all of the electrons.
Yeah.
It would, yeah.
Yep.
None of them would pass.
Right.
Yeah.
Basically, you would stop the whole electron flow from the cathode to the plate. And that's actually as a term. It's called cutoff.
Okay.
Which makes sense.
Yeah.
Right?
Yeah.
You're cutting off the electron flow. Now, you can see, now from what we've described so far, that if you put a varying voltage, and it could be, let's say it's audio, because we're audio guys, on that grid, what's that going to do to the electrons going through?
It's going to be a constantly changing flow.
Right.
Yeah.
Yeah. So the number of electrons that get through will be theoretically proportional to the amount of negative or positive voltage on that grid, right?
Yeah.
Now, if the grid goes positive, what happens?
It's gonna attract. It's gonna increase the flow of electrons.
Well, it could, but the main thing it's going to do is act like this sort of miniature crummy plate in the tube, and that's sort of messes up our whole concept.
Yeah.
So in general, you need to keep that grid voltage always negative.
Okay.
And then we create a new problem, because if we're putting an audio signal into the grid, which is varying above and below zero, if you ever look at the waveform,
Yes. Yeah.
You'll see, let's assume a sine wave, which is symmetrical.
Sure.
Half of it's a positive, and half of it's a negative.
Yeah.
So only the negative part is going to have any control over the electron. So basically what you're going to end up with is kind of a rectifier again.
Yeah.
Sort of a dynamic rectifier, but it's not going to do what we want it to do. Because what we want it to do is what?
Amplify?
Exactly. Yeah. What we want is an amplifier.
Yeah.
Just like if you're running a hydroelectric dam and you have this huge amount of water coming down the river and you need to control the amount of water that gets through the dam, to generate the proper amount of electricity and not drive things crazy or not have too little to make it work.
Yeah.
You have to control that. And essentially they do that with a valve.
Yeah.
I mean, it's gigantic scale valve.
Yeah.
But that's the concept. We're doing the same thing.
Yeah.
So they can use a relatively small gate, in the dam to control a huge amount of water.
Yeah.
So we can do the same thing with a vacuum tube. So we can take a small signal and make it larger, which, that's the definition of an amplifier.
Yes, yeah.
Right? So we start out with something like a microphone output, which is really, really small. Like right now, you and I are sitting on opposite sides of a ribbon mic, and, that's essentially a generator.
Yeah. Yeah.
in a very simplified kind of way, but it's generating a minute. We're talking about really, really tiny voltage. That is useless.
Yeah.
We can't do anything with it.
Yeah.
You can't put a pair of headphones on an output of a mic and hear it.
Yeah.
We need to amplify that. So the thing to do is to put that microphone signal into the grid of the tube.
Yeah.
And when we do that, we can vary the number of electrons that get through to the plate. Now, the minute voltage on the grid is measured in millivolts.
Yeah.
Thousandths of a volt.
Yeah.
But typically, how much voltage do we use on the plate?
Hundreds.
Right.
Yeah. Like 200 or so.
Yeah.
Yeah.
Yeah, it depends on the circuit. I mean, some could be as low as less than 100 volts, and some could be thousands of volts.
Yeah.
But for our purposes, it's usually in that 100 to 300 volt range. And so now we're varying that, we'll call it 300 volts. And we can go all the way from 0 to theoretically 300 volts on that plate.
Yeah.
Just by varying that grid voltage.
Yeah.
But we do run into a problem, and that is the effect of the grid on the number of electrons getting through is not a linear function. So in other words, if we increase, I'm going to use bigger voltages just for the sake of example.
Sure.
If we have 1 volt on the filament, on the grid of the tube, if we increase that to 2 volts negative, or decrease it -2, depending on how you want to look at it, but we've increased the voltage in a negative direction, then that's going to permit fewer electrons to get through. But it's not necessarily going to cut them in half.
Okay.
So it might cut them down, 10% or something.
Yeah.
The output of the tube on the plate is not a good representation of what went into the tube. What do we call it when the input and output have different characteristics?
Like the voltage change, you mean? Or
Distortion.
Oh, I see.
Yeah.
Yeah.
And a very broad term, distortion.
Yeah.
Because we've taken that original pristine waveform from our microphone, now we've messed it all up.
Yeah.
And the same thing if we keep going negative, even before we get to the point where no electrons get through, it gets to a point where increasing the negative voltage doesn't decrease the number of electrons getting through in a linear way.
Yeah.
Again.
Yeah.
So there's never a time where the amount of voltage on that grid is an exact control of the plate voltage.
Mm-hmm.
It's always somewhat distorted.
Yeah.
It's inevitable.
Mm-hmm.
And, we're talking about vacuum tubes here, but the same thing applies to any amplifying device.
Mm-hmm.
So we've got a problem
Mm-hmm.
because we have to have our grid voltage from our microphone in that optimum range.
Mm-hmm.
Well, it's not going to be. It's millivolts, and we
Yeah.
need volts. So what we have to do is superimpose on that audio signal some direct current,
Mm-hmm.
negative voltage. And you know what that's called?
That's the, what is that called? I do know that.
Okay.
No, I can't remember right now.
Okay, that's called bias.
Right.
Bias.
Right.
So if you were to draw a graph
Mm-hmm.
of a, let's say, and everybody can look at this, I'll post some version of this drawing for you to see. If this on the x-axis, the horizontal axis,
Mm-hmm.
is the grid voltage,
Mm-hmm.
and on the vertical axis, the y-axis, is the plate voltage,
Mm-hmm.
a perfect amplifier would just be a straight line.
Yeah.
So 0 and 0 would be 0 out, and then up to the maximum.
Perfectly linear. Yeah.
Yeah. About the only thing in the universe that does that is a piece of wire.
Hmm.
I mean, even that probably has some small degree of
Yeah.
non-linearity or distortion, but essentially you can presume a piece of wire
Mm-hmm.
is perfectly linear like that.
Mm-hmm.
But, a piece of wire isn't very useful. It doesn't get signal from one place to another, but in our case, we want to make it bigger,
Yeah.
and that's not going
The
to
wire
do
can't
it.
do that. Yeah.
So if we were to look at and this is not necessarily of any particular tube, but this is just sort of generally the way it works. The way the tube input and output goes looks more like this.
Mm.
Okay, it's sort of like a elongated S.
Yeah.
And you can see down at the low end of the grid voltage,
Mm-hmm.
it's changing a little bit, but plate voltage isn't changing much at all.
Yeah.
So that's not right. Same thing when we get up to the high end of it.
Mm-hmm.
Eventually, the grid voltage, and this is in the negative direction.
Mm-hmm.
When we get to the high end of it, again, it becomes nonlinear. So we're getting fewer electrons through.
Yeah.
So not really useful at either
Yeah.
extreme. But there is a section, relatively narrow in between, where it approximates that perfect 45-degree angle that you would
Okay.
have if you were to diagram a wire.
Yeah.
The input and output would be in exactly the same ratio. So when the voltage doubled on the grid, the plate voltage would double as well.
Yeah.
What we need to do is to move our little minute audio signal up here into this range where the tube is most linear,
Yeah.
where it has the least distortion. And the way to do that is to impose a negative voltage on the grid.
Mm-hmm.
So it starts at the point where it's relatively linear.
Mm-hmm.
And you can allow it to go up to where it stops becoming linear. But you've shifted everything up.
You kind of shifted the starting point. Yeah.
Right. Yeah. So that's the function of bias. Okay. Now, traditionally, in the early days of vacuum tubes, everything was run off of batteries. They didn't really have much in the way of AC powered stuff.
Yeah.
It just wasn't practical.
Mm-hmm.
And even then, early 1900s, most people didn't have electricity.
Yeah.
So everything ran on batteries. And they would use one battery for the filaments, another battery for the plate voltage, and a third battery to provide this bias voltage.
Okay.
Okay. Filaments don't need much voltage. What do they usually require to operate?
Either somewhere between 6 and 12
Yeah,
volts. Yeah.
typically, yeah. Most tubes are designed for 6 or 12 volts on the filament. And when you look at the name of a tube, the model number of a tube, those first one or two digits specify the filament voltage.
Yeah.
So A 12AX7 requires 12 volts.
Yeah.
Low voltage.
Mm-hmm.
Needs a bit of current, though.
Current, though, yeah.
Yeah.
Higher current.
But we don't have to light up that filament like a light bulb.
Mm-hmm.
You know, we don't need it bright,
Yeah.
light up the room.
Yeah.
We just need it to emit electrons.
Yeah.
And we also want that filament to last as long as it can.
Mm-hmm.
The voltage is kept fairly low.
Mm-hmm.
You know, for the life of the tube, it's important to keep that voltage fairly constant.
Mm-hmm.
That's why in the products, the DW Fearn products, we always use regulated DC voltage on the filaments.
Mm-hmm.
That makes the tubes last a whole lot longer.
Yeah.
You know, people that are used to guitar amps, or if you go back, if you're old enough to remember vacuum tube television sets,
Mm-hmm.
you know, it was like this constant replacing tube.
Yeah. Yeah.
You know, because many things go wrong with the tube over time, but
Mm-hmm.
the filament burning out was one of the things
Yeah.
that could happen. So there we need that low voltage, 6 or 12 volts for the filament. And, I mean, they make tubes with much higher voltages too, but, you know, for our purposes, 12 volts is pretty common.
Yeah.
For the bias voltage, we have to look at the characteristics of the tube, and every tube is designed a little bit differently,
Mm-hmm.
and say, well, here's the point where it becomes relatively linear,
Mm-hmm.
you know, where the input and output rise and fall exactly together. So we need this much bias
Mm-hmm.
right here. We can, you know, use a battery to do that,
Mm-hmm.
or another separate power supply
Mm-hmm.
to do that.
Yeah.
And there's nothing wrong with that. That works fine.
Mm-hmm.
But it adds complexity, and there's simpler ways to do it.
Yeah.
We have to look at the tube now, and for this I'm going to bring out the schematic of this simplified version of the prototype you just built.
Mm-hmm.
I eliminate a lot of this stuff to make it easier to
Sure.
understand. You know, we've got an input transformer that goes more or less directly into the grid of a vacuum tube.
Mm-hmm.
And we have a plate voltage, in this case 268 volts. It goes through a resistor. And then we have the cathode. And
Mm-hmm.
normally you would think the cathode would be grounded because that's sort of the reference point. You know, when we talk about ground,
Yeah.
it's a little misleading because when you think of ground, you think of the earth.
Mm-hmm.
You know, you think of a ground rod pounded into the ground.
Yeah, you think
know.
of nothing. You think of, an end point, right?
Right. And that's not technically what we're doing here.
Mm-hmm.
You know, these circuits don't need to be connected to the earth to function.
Mm-hmm.
You know, otherwise satellites wouldn't work.
Mm.
Stuff in airplanes wouldn't work.
Yeah,
You
yeah.
know, so it's not necessary to connect to the earth.
Mm-hmm.
In fact, the only reason to connect to the earth for our purposes is for safety.
Mm-hmm.
You know, if there's a fault in the wiring, the AC wiring, that'll trip a circuit breaker and keep you from getting killed,
Mm-hmm.
or from lightning. You know, if lightning
Yeah.
hit the building and found its way into your audio wiring, it could blow up all your equipment.
Yeah.
So by having a ground reference, and that's a whole other discussion of how you protect stuff in those situations, but ground itself is not necessary to make any circuit work. When we talk about ground in this discussion, we're really talking about a common point.
Mm-hmm.
You know, we could draw this schematic diagram with all these ground points, and you can see there's a lot of them,
Mm-hmm.
all connected together by wires.
Mm.
And that would actually give us a much better conceptual view of what the circuit is.
Yeah.
But that makes the schematic really hard to follow.
Yeah.
It's just a lot of wires running all over the place.
Yeah.
You know, say, where does this go? Where does this go? Where does this go? And you'll see on some schematics where they will have, one usually heavier drawn line
Mm-hmm.
running through the schematic, maybe
Yeah.
down the center of it,
Mm-hmm.
that's connected to ground. Then you see everything connected to that.
Mm-hmm.
And that sort of makes it easier to understand.
Yeah.
But we just have to know that where something's connected to ground is just a wire connecting every other place that has
Mhm.
that ground symbol. You know, on my schematics, I still use the traditional ground symbol.
Yeah.
Technically, what I should use is, what's called a chassis ground
Mhm.
symbol, which is a little bit different
Mm-hmm.
format symbol. but I don't.
Yeah.
I've been doing this for
Yeah,
60
yeah.
years. I'm not about to change. So we have to remember that all those grounds are all connected together.
Mhm.
And in this case, if we had the cathode grounded, we would have our electrons flowing from the heated cathode passing through the grid with its varying voltage to the plate.
Mhm.
And the plate has a high positive DC voltage on it.
Mhm.
But there's nothing that says the cathode has to be grounded. And we have to think of this in terms of the relationship between the grid and the cathode. If the cathode is grounded and we put a negative voltage on the grid, then obviously in relation to the cathode, the grid is more negative than the cathode.
Yeah, yeah.
So what we can do is raise the cathode above that ground potential, that zero ground potential.
Okay.
And what do we use for that?
Yeah, resistor.
Yeah, a resistor. Now, if you put a voltage through a resistor, what's one of the characteristics that you can measure?
That it'll drop the voltage.
Exactly.
Yeah.
Yeah. So whenever a current flows through a resistance, there's a voltage developed across it.
Yeah.
And that voltage is dependent on the value of the resistor and the amount of current flowing through. Okay, it's Ohm's law.
Yeah.
Which we won't get into right now
Yeah.
because I know you understand that.
Yeah.
And so if we figure out what that resistance has to be to raise that cathode by that same amount as the bias we were talking about,
Yeah.
we've solved that problem without having a separate power supply. Okay?
Yeah.
And so that makes the circuit a lot simpler.
With just a resistor instead of
Yeah,
an entire separate power supply. Yeah.
right. Now, if there were an operational advantage to using a dedicated bias supply, I would do that because I don't like compromising on anything. And, if it costs a little more, it costs a little more. That's the way I design stuff.
Yeah.
But doing this has other advantages,
Yeah.
which we'll talk about, maybe not today, but at some point. There's benefits to doing that, okay? So now we've changed the relationship between the cathode and the grid by that, what we've determined to be the optimum bias voltage.
Yeah.
And it just works,
Yeah.
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 It's very simple.
Yeah.
But now, if we don't have anything connected to the plate, let's just say it just connected to our high voltage, right? Nothing would happen. The electrons would go in and come out, and we'd extract no useful information from it. So what we have to do is somehow get that voltage out of the plate that's now been amplified so we can use it.
Yeah.
So the way we do that is another resistor. In this circuit, there's a couple of them just because, for reasons we won't go into now. But we can think of this as just one resistor that goes from the plate to our source of high voltage. Okay? And now we've got the high voltage going through this resistor and dropping the voltage somewhat, right? Because it's a resistor.
Yeah.
And when there's current flowing, there's a drop in voltage. And we can measure it across that resistor. But at the same time, at the junction between the plate and that resistor, we can extract our amplified audio signal.
Yeah.
So it's important that we have that resistor there. Otherwise, we have no audio.
Yeah.
Right?
Yeah.
So we have to have that, what's called the plate resistor, not surprisingly, plate resistor. And the value of that resistor is critical, just like the value of that cathode resistor is critical. All right? And those two things sort of determine the characteristics of that amplifier stage. Then there's one more thing. And if you look back here on the grid, there's also a resistor that goes to ground.
Yeah.
Right? And you'll see in each of these stages, there's a resistor to ground.
Yeah.
When you put your minute voltage into the grid, right, if no current's drawn, there's no voltage really developed, So we have to have at least some resistance there for a voltage drop, to supply the grid.
Yeah.
That's not always true, but in the kinds of circuits we're talking about, You need that
That's
grid
the case.
resistor.
Yeah.
So cathode resistor, grid resistor, plate resistor all have to be in harmony, and changing one means changing the other,
Okay.
or the other two, most likely. As a general rule, just as, conceptually, the cathode resistor is relatively small value resistor because we don't need much voltage, few volts
Yeah.
across that. So that resistance value is very low. The plate resistor, on the other hand, has to be pretty high,
Yeah.
in order for us to get some useful work out of it. So the cathode resistor might be typically 500 to a couple thousand ohms, in most cases. The plate resistor is probably in the tens to hundreds of thousands of ohms.
Yeah.
And the grid resistor typically is also in hundreds of thousands of ohms. Now, in this case where we have a transformer feeding it, it changes the whole concept a bit because, and we won't go into that in detail, but, the transformer is a different animal,
Yeah. Yeah.
and it has impedance, which is the alternating current version of resistance, So it sort of throws off our concept here because it's transformer. But normally that resistor would be very much larger. In this case, it's relatively small, about 2.5K, because that's what the transformer needs to be loaded with in order to have its flattest frequency response and best dynamic range.
Yeah.
Now, we've got our transformer signal coming from the microphone, going into the grid of the tube. We have our bias voltage on the cathode, which makes the tube more linear. And as that varying voltage on the grid now is controlling a much higher voltage, millivolts now are controlling hundreds of volts, and we have lots of signal coming out of here.
Yeah.
We've amplified it.
Yeah.
Now, typically a stage like this would have what they call an amplification factor,
Okay.
meaning how much it's multiplied
Yeah. Yeah.
in the range of 10 to 40.
Okay.
Okay, so what's coming out is 10 times bigger or up to 40 times bigger.
Okay.
Now, if you take a tube like a 12AX7, which I hate, I was probably 12 years old when I developed my dislike for the 12AX7.
That young?
Yeah.
Wow.
Because it never sounded good to me. And in that case, that was a design decision based on the economics of building consumer equipment. Because that has a huge amplification factor.
Yeah.
I forget what it is, but it's 40 or 60 or something like that. It's really high. When you do that, you just introduce so many problems into the circuit. It becomes potentially unstable. It's just trying to make it do too much. So a much better approach is to use two stages. One that amplifies it, say, by 10 or 20, and another one that amplifies it by 10 or 20. And then you've got, a robust signal you can do other things with.
Yeah.
And we've created an amplifier.
Yeah.
And by making sure all these tubes have the right cathode, grid, and plate resistor, we make sure they're operating in that optimum range, so they have the minimum distortion.
Yeah.
Now, to get from one stage to another, we could, theoretically, we just connect the plate of this one to the grid of this one. But now, all of a sudden, we put a couple hundred volts on the grid of the next stage, positive. It's just going to act like this new little plate we put in there, and it's just not going to work.
Yeah.
So we have to change from this DC with the amplified audio and superimposed on it and filter out the DC and just give us the audio signal.
Which is what the capacitor's for.
Exactly. So one of the characteristics of a capacitor is that
it blocks DC.
Right.
Yeah.
Yep. DC can't get through, but choosing the right value, it will allow audio signal to go through. So the value of that capacitor is also critical because if we don't have enough capacitance, it'll roll off all the loads. We can make it bigger and bigger. There's a point where it's like, well, that's going down to practically 0 hertz. We don't need to go any bigger than that.
Yeah.
So we pick a value that provides us with good low-frequency response.
Mm-hmm.
The highs, generally speaking, are going to take care of themselves through
Mm-hmm.
the capacitor. If you use good quality capacitors, the right type. There's other factors that go into this, aside from just making sure we have good frequency response through that
Mm-hmm.
and blocking the DC, because whenever you put an audio signal through a capacitor or an inductor for that matter, you'll have a phase shift. And I don't want to get into too much detail on phase shift at this point, but it is important.
Yeah.
And what that means is that the audio signal passing through, which originally had some coherent phase to it, the obvious example of a phase problem was something that's 180 degrees out of phase, which is the phase or polarity switch on your mic preamp.
Yeah.
Which can be useful if something's backwards and you can correct it so you don't have cancellation from two mics.
Yeah.
But a capacitor is a frequency selective device. So its phase shift can vary with the frequency going through it. So what's the problem there? Because musical sounds are not pure tones. They consist of the fundamental frequency and then what else?
The harmonics.
Right, harmonics are overtones.
Yeah.
So we want to make sure that the phase relationship between that fundamental and all those harmonics
is
the
preserved.
same.
Yeah.
The sonic benefit of that is that the instruments sound real because we preserved that original phase relationship between all the fundamental and all the overtones. But the instruments also sound much more solid.
Yeah.
When the phase gets messed up, it does strange things to the way things sound. And it's subtle.
Yeah.
It's not something like distortion or something with a lot of distortion. You hear it right away.
Yeah.
The phase distortion is a whole different kind of thing.
Yeah.
And it's more of a feel thing. It's like, that just doesn't feel like it should.
Yeah, and it's maybe the type of thing where across a bunch of different tracks across a recording, if they all have those subtle phase issues, it's a feel thing.
Right.
It would start to sound just not quite right, maybe, and you couldn't really put your finger on it, that kind of thing.
Exactly.
Yeah.
Yeah, good description. We normally think of our hearing range of 20 hertz to 20 kilohertz, right? And most people can't hear above 20 kilohertz, especially as you get older. And even young people today, because you've been subjected to so much loud music and earbuds and stuff like that. The first thing to go in your hearing is the high frequencies. So I know lots of people that aren't even 20 years old that can't hear above 10 kilohertz, which is not the end of the world, but it does indicate that some damage has been done. But let's presume that you have good hearing, you can hear up to 20 kilohertz, and we preserved the phase relationship all the way through to 20 kilohertz. But then above that, it starts to go haywire. You can't hear that, right? But at least some of those overtones are described by a waveform, which is made up of all those frequencies you can't hear. So even though you can't hear them, they affect how the sound sounds. Isn't that interesting?
Yeah, that's very interesting. Yeah.
So it's really important that you don't just worry about the phase response up to 20 kilohertz.
But past.
So you want to make it as uniform a phase response as high as you can go.
And is it the same for the lower end?
Exactly.
Okay.
Yep. So in the low end, that's even more challenging because we live much closer to that low end in the world of music than we do in that high end. Something like a bass guitar or even a double bass or organ pedals and stuff that go down to 40, 20 hertz. If you've messed up the phase relationship between that 20 hertz fundamental and the harmonic at 40 and the harmonic at 80 and so on, it's not going to sound the same. And that's very challenging to make sure that we get that phase response at the low end as good as we can make it.
Yeah.
I mean, nothing goes below 0 hertz.
Mm-hmm.
It's undefined.
Mm-hmm.
But we need to extend our low frequency phase situation so that we do minimal damage to that bottom octave or two.
Mm-hmm.
So that's important too.
Yeah.
Now, if we have a circuit that rolls off, say at 20 hertz,
Mm-hmm.
and the response now is becoming lower and lower,
Yeah.
then we've got another problem, because by rolling off a frequency, not only do you lose that information,
Mm-hmm.
but you've also distorted the waveform, just like you did on the high end, because that waveform is defined by, the phase and amplitude relationship of that fundamental tone, and of course all its harmonics. So we want to make sure that not only do we not mess up the phase, but we want the frequency response to go as low as we possibly can.
Yeah.
This circuit, even with the transformers, has a point where the frequency response drops 3 dB at 0.5 hertz,
Okay.
half a hertz.
Mm-hmm.
That energy down there is not useful. In fact, it can be problematic.
Yeah.
Because there can be vibration and weird things.
Mm-hmm.
I remember when I first developed the VT1 mic preamp, the first studio I put it in, and we were experimenting with it. Everybody was pleased with the way it sounded and everything. We were in a control room listening. There was a guy out in the studio, and he came up to the window. It was a big studio with a really big window.
Mm-hmm.
And he leaned against the window, right?
Yeah.
And we saw the VU meters go
Oh.
like that,
Huh.
It was like, what was that?
Yeah.
We finally figured out it was him pushing that glass. Now, how much did that glass move?
Yeah.
Practically nothing. I mean, it's pretty solid.
Yeah.
But that was enough to put this pressure wave through the room that the mic preamp was
picking up.
picking up.
Wow.
So
Wow.
that's the problem end of doing that,
Mm-hmm.
because there can be things in the audio that you didn't expect.
Yeah.
And we couldn't hear it in the speakers,
Mm-hmm.
although they were monitors without any grill cloth on them or anything, so we could see the cones, see the cones go in and out.
Yeah. Wow.
So that's the downside of that extended low frequency response.
Mm-hmm.
But it's a trade-off.
Yeah.
And chances are throughout the process it's going to go through other gear that doesn't have that kind of response, so it's going to get rolled off anyway.
Yeah.
And you may end up putting some EQ and cutting out some of that low end.
Yeah.
So it doesn't end up being a problem on a finished recording, but it's there for you to use if you need it.
Yeah.
Let's move on with this. We've got now 2 stages of amplification, which are very similar. You can see they look pretty much the same. And then we have another capacitor from the plate of the second stage going around to the grid of the next stage. In this case, we have a resistor here, the grid resistor, but in this case, it's what?
It's it's variable to potentiometer.
Right. What do you suppose the purpose of that is?
Well, it's a gain control, right, or a volume control. So
Yep.
it's giving you control over how much of that signal is getting to the grid.
Right. Yep. So if we turn this all the way down so that the arm of the pot is down at the bottom, we've essentially connected the grid to
Ground.
ground.
Yeah.
So no signal.
Yeah.
We shorted it out.
Mm-hmm.
That's what happens when you turn something all the way down,
Is you're just shorting it.
basically.
Mm.
I mean, it's not hurting what's feeding it because
Yeah.
it's going through this whole resistor regardless.
Yeah.
We're just tapping off a certain amount of the voltage that we need to go to the grid of the tube.
Yeah.
And, this stage is very simple, just a cathode resistor, grid resistor, which is variable in this case, and a plate resistor going to our high voltage. And so far we've only been talking about triodes, and it's called a triode. You know why?
Yeah, because there's 3 electrodes, right?
Right. But, if we look at our triode, whoops, where'd it go? Here it is. And I didn't draw the filament.
Really,
in this
there's
There's a filament, a cathode, a grid, and a plate.
There really are 4.
There's really 4. But since the filament and the cathode work together
Kind
as
of
one unit,
yeah.
we just consider them one element in the tube.
Yeah.
Circuit-wise, it's one thing.
Yeah.
There's 3 elements. But we can put more grids in there.
Mm-hmm.
Do you have any idea what the advantage of putting more grids in would be?
I know they can serve different functions, right? Because there's different names for them.
Mm-hmm.
There's suppressor grid, I remember.
Right.
There's another one.
Screen grid.
Screen grid.
Yeah.
Yeah.
Yeah. So if you have a tube that has, start with a triode,
Mm-hmm.
and we have the grid, which we've been calling the grid all along here because it's the only one.
Yeah.
But when we start talking about
Adding more,
we got to give them all names.
Name them, yeah.
So that grid is called the control grid.
Right.
For obvious reasons.
Mm-hmm.
Right. If we put another grid in there, it's called the screen grid.
Mm-hmm.
And the purpose of that was because what they discovered, and it's not an issue for this kind of circuitry, but when you're dealing with higher power,
Okay.
what you had was the electrons emitted from the cathode being controlled by the control grid and hitting the plate. And what they found was when you're drawing a lot of current because you're driving a speaker or something, some of those electrons got bounced off the plate. They didn't get all absorbed by the plate and transferred into the circuit.
Yeah.
But they actually, what they call secondary emission, where it became, in essence, another cathode inside the tube. That was messing everything up.
Yeah.
So if you took another grid in there, and remember these are all concentric in the way they're built,
Yeah.
And put that in there, it acted sort of like a shield between the grid, the control grid, and the plate.
Okay.
And you put a positive voltage on that screen grid, but much lower than the plate
In the
voltage.
plate. Yeah.
And what that did is essentially just said, keep them moving, keep them moving, and then that way they didn't bounce off of there and come back and cause problems within the tube. So that's a tetrode.
Okay.
You don't find many tetrodes.
No, I don't think I've ever seen one.
In transmitters, radio frequency transmitters, they use tetrodes a lot, because they're very efficient.
Yeah.
And a tetrode has more intrinsic gain than a triode, just because of the nature of the way the electrons are flowing.
Yeah.
So, in a transmitter, for example, that might be putting out tens of kilowatts of power, they often use tetrodes because that way they can, draw lots of current through that tube without causing a problem with the electrons getting back to the grid and cathode and causing problems.
Yeah.
Another interesting thing you can do with a screen grid is by varying the voltage on it, you can vary the gain of the tube over a range, not like from 0 to maximum, but you can control the gain of it somewhat. And that's useful in a transmitter for adjusting the amount of power.
Yeah.
Doesn't have much application in audio. Okay. What you're more likely to find in an audio circuit is a pentode.
Yeah.
Those are usually the output stage tubes, the 6B6s, 6L6s, KT88s. I mean, all those tubes are all what they call pentodes, and they're usually what they call beam power pentodes. In this case, this last grid serves a very, very different function. It's basically a thing that channels the electrons to the plate, and instead of like the screen grid keeping them from getting out of control, it just sort of focuses them on the plate. So you get the maximum amount of electrons getting to the plate and not going astray. So they call them beam forming plates in some of those tubes because they're designed in such a way that, they corral the electrons to keep them going. Tubes are great. You can understand what's going on inside them.
Yeah.
You look at a transistor and it's like, I don't understand what's going on in there.
Yeah, piece of plastic. Yeah.
Yeah. I mean, conceptually, they're very similar. And the principles are very, very similar.
Yeah.
But just in terms of taking one apart and looking at it, you can tell how a tube works.
Yeah.
Taking it apart.
Yeah.
Can't do that with a transistor. That's too meaningful.
Yeah.
And anyway, those beam-forming plates are generally connected directly to the cathode of the tube. And that seems to work best. In some tubes, that third grid, which is called the suppressor grid, comes out on a separate pin on the tube, so you can do other things with it. But generally, it's connected back to the cathode. But it is available if you need to use it for some other purpose. Yeah. There's even tubes with more grids, but they're pretty rare.
Yeah.
There's tubes with 5 grids, 6 grids.
And those are probably made for very specific purposes.
Right.
Yeah.
Yeah. There are tubes that combine many functions inside one tube.
Yeah.
And not really used in audio.
Yeah.
Oh, I did want to mention about the way tube numbers are derived.
Right.
A typical tube number, let's take a 12AU7. Tubes used in audio from time to time. It's a dual triode.
Right.
And the first 2 numbers are the filament voltage. So we know that is a
12-volt.
12-volt tube. And last number is the number of elements in the tube. So in this case, we have 2 triodes.
Yeah.
Plus a filament. So we have 7 elements total.
Yeah.
So all those tubes that start with 12, end with 7, are dual triodes.
Yeah.
There may be some exceptions, but basically that's true. Okay. If they're in that A series, 12A7, 12AU7, T7, X7, Y7, they're all dual triodes.
Yeah.
7 total elements inside.
Yeah.
Other tubes, like something like a 6AU6, would have a 6-volt filament and 6 total elements in the tube.
Yeah.
Other than that, there's not a whole lot the tube number tells you.
Yeah. Is it lettering is kind of...
I think different manufacturers had different concepts of that.
Yeah.
So the 12A series are all dual triodes.
What is the older tubes that are the octa ones?
The
SN series?
Yeah.
Yeah.
Yeah. It's interesting that most of those old tubes, like 6SN7, 6SL7, 6L6, all those tubes have a miniature tube equivalent.
Really?
Yeah. So I would have to look it up to tell you for sure. It's either, I think it's the 6SN7 is functionally equivalent to a 12AX7.
Really?
Yeah. So when the so-called miniature tubes were developed in the 1940s, they basically wanted a smaller version of these much larger tubes.
Yeah.
So they just scaled them down, gave them a different number, but same characteristics.
Yeah.
Basically same.
Yeah, I didn't know that.
Yeah. So we've talked a lot about tubes. So
Yeah.
you think you've learned something?
Oh, absolutely. Yeah.
Good.
Yeah, definitely.
Okay, good. Well, thanks for sharing this discussion with the listeners.
Yeah, thank you. Yeah. No, this has been great.
Yeah. Well, maybe we'll do some more.
Yeah, I'd love to.
Okay.
Yeah.
Great. Thanks, Matthew. This has been an informal lesson that I gave to intern Matthew Glosson. I hope you found it useful. As always, thanks for listening and thanks for your comments. I can be reached at dwfearn@dwfearn.com. This is my take on music recording. I'm Doug Fearn. See you next time.